Our next Extension 2 topic is proof. And the language of logic is the language of proof. It's a very logical thing. So let me define a few things before we take this journey into proof. Everything starts with a proposition. And a proposition is simply a sentence that proposes an idea. Now the wonderful thing about logic is very black and white. Yes or no. It can either be true or false. Can't be both. There's only one of two values you could take. It's the basis behind computing as well, and that's why they use binary, 0 and 1, on and off, same sort of idea. So, it is raining is a proposition. Could be true, could be false. As opposed to something like this, is it raining? Just a subtle change of a couple of words there. It's no longer a proposition, but of course now it's a question. Now logic is what we're interested in. Now logic has its own language and it has its own alphabet. And the letters in this alphabet are what we call propositional variables, and they're represented by pronumerals, which in essence are letters anyway. But it could be any symbol. So P1, P2, often done because P standing for proposition, so proposition 1, proposition 2. But it doesn't have to be P, it could be X, Y, Phi, it doesn't have to be English letters, it could be anything. Right. Then we have punctuation, again just like any other language, and we really only have two, and they're the parentheses. We use those to punctuate things. There are a couple of others, but generally it's a punctuation symbol. And then we have these things, the logical symbols, our connectives, what connects all of the statements, all of the propositions. And here are the ones we will see. Arrow. Now technically it's the double arrow, so you see two lines. People do sometimes just draw a single arrow, and that's fine, but technically the double arrow is implication. And that's for our if-then statements, the heart of a deductive proof. If this happens, then this happens. The negation symbol, so the hook, very commonly used. Sometimes you'll see a tilde used for a negation, and it's the complement of a proposition. The double-ended arrow is the equivalence. So they're if-then statements that work in both directions. So propositions that are equivalent logically to each other. For want of a better word, the A without the horizontal bar, that sign there, what do we call it? It's a caret, that's right, isn't it? If you put it above a letter, we call it a caret. Okay, so the caret symbol, but it's much bigger than the caret symbol, represents and that's the conjunction of two propositions. That upside down is or the disjunction. Now that's very similar to set notation, if you think about it, intersection and union. And it's the same thing, because intersection is, well, what do they both have in common? So that's and. Union is, you can have this or you can have this, so them joined together, that's the or. So same sort of thing, but instead of being a curve, it's a straight symbol. And then we have these quantifiers, and the two quantifiers that we see is the backwards E, which represents there exists, and the upside down A, which represents for all. So they're our quantifiers where they use. So there's our alphabet and language behind the logic. So that brings us to a statement. Now a statement could simply be a proposition. A proposition is a statement. Or of course it could be a series of propositions that are connected by the punctuation symbols and the logical symbols that we see. A logically valid argument. So a list of propositions, so you have a whole list of propositions followed by a conclusion. That essentially is a proof. If you go back to the first type of proofs you saw, which I guess was in geometry, you'd have a series of propositions. This angle equals this angle equals this, and so on. And then you come up with a conclusion. Therefore, these triangles are congruent. That's basically what you're doing. You're putting together a logically valid argument. So a list of propositions and finishes with some conclusion. Example. Now this is not an example of the logically valid argument. This is a definition of example. So example is simply a situation that demonstrates the proposition. So an example of it happening. More interesting is counter examples. And counter examples are great because it demonstrates that a proposition is not always true. So they're great because if you want to disprove something, all you've got to do is find one counterexample. Find a counterexample, bang, that proof's no good. So we often use counterexamples to invalidate an argument or a proof. Let's talk a bit about negating or negation. Basically, it just changes the value. Remember I said it could only have one of two values, either it's true or false. So negate it would be to change its value. Turns a true statement into a false statement into a true statement. That's the negation of a statement. Now, some things that are logically equivalent. If you want to negate x and y, that would be the same as saying not x or not y. So if you think about it, if you don't have x and y, then you must have either no x's or no y's. So they are logically equivalent. If you had to prove something was the negation of x and y, you could instead prove the negation of x or the negation of y. You could do that. And the reverse of that. So if you wanted to negate x or y, the logical equivalent then is that you don't have x and you don't have y. Right? Because we're saying, I don't have x or y. Oh, well, I don't have x and I don't have y. Neither case could be true. Okay, the negation of for alls and there exists. To negate for all is the same as there exists the negation. So if you're going to negate for all x something is true, you're going to negate it, that's the same as saying, well, hang on, there exists one such that A is not true. Because it's not true to say that for all x, this statement is true. So there must exist an x, doesn't have to be a whole heap, could just be one, the counter example. There exists an x, the colon often means such that. There exists an x such that it's not, that statement is not true. And the reverse is true as well. So if you want to negate the there exists situation, well, that's the same as saying, well, for all x, the negation of the statement. So that's just how we can play with negations. Let's look at some examples of that. So I'm going to make a statement that the number is even, is my statement. The number is even. Well, 6 would be an example there where that statement is true. That is true. The negation of x would be the number is not even. Don't fall into the trap of thinking, oh, it means the number is odd. Well, no, that's not true. The negation is that it's simply not even, because you could have negative numbers, you could have fractions, you could have irrational numbers. And none of those are even as well. So it's not simply saying, oh, it's odd. It would be the number is not even, and 6 would now be false for that statement, because 6 is even. So it would be false to say 6 is not even. All birds are black. That's my statement. All birds are black. To negate that one, well, there must be at least one bird then that is not black. As soon as I find one counterexample, then I know my statement is false. So I've changed a true statement into a false statement. There are other ways we could say it. I could have said, not all the birds are black. That would be a negation of it. Or I could say, well, some birds are not black. This is using the language. It's the negation of it. Let's have a look at one of those there exists statements. So there exists an x, which is a real number. Remember, that's the element symbol from some notation. Which is a real number such that x squared is less than 0. Now remember, the statement can be false. It's just a statement. And of course this one is false, because what we're saying is there exists a real number such that its square is negative. And we know that's not true. You can't square a real number and get a negative number. So this particular statement actually is false. But it's still a statement. You can still make that statement. It's just that its value is false. Well, the negation of that then becomes, for all x that are real numbers, x squared is greater than or equal to 0. That would be the complementary case of that. So what we're saying is, well, for all real numbers, their squares are actually greater than or equal to 0. And that would be true. And that is our negation. So to negate there exists, it turns into a for all statement, and then we give the complementary result. The complementary result to x squared being less than 0 is that x squared is greater than or equal to 0. Implication. So our if-then statements. If-then statements. So P, Q. If P, then Q. P implies Q. So that's what we're saying. If P is true, then Q must also be true. Because P implies Q. P implies Q. Now, P is what we call the premise of the implication, whereas Q is our conclusion. If my premise, I've got my premise, then I can conclude that I've got Q. P implies Q. P is a sufficient condition for Q. So what do I mean by that is, well look, Q can still exist without P. Just because you've got Q doesn't mean you have P. However, if you do have P, then you must have Q. Because P implies Q. Every time I see P, I must have Q, because P implies Q. So therefore, having P is sufficient to conclude I've got Q. And that's why we call it a sufficient condition. Q becomes a necessary condition for P. A necessary condition for P, because P cannot exist unless Q exists. Because remember, every time we see P, we've got Q. Therefore, P can't exist unless we get a Q. Because if I've got P, bang, I must have got a Q. P implied Q. Unless Q exists, I mustn't have had a P. Q is necessary for P to happen. A nice example of that, I've got two statements here. X, you score 90% or more in extension 2, and Y is the statement, you always listen to your teacher. Well, I claim that X implies Y. Okay? If you score 90% or above in extension 2, then you always listen to your teacher. This is the implication. It must have happened. Okay? So scoring 90% above is sufficient to conclude that you listen to the teacher. That's what this would say. So it's sufficient for that. P is sufficient for Q. And the necessary condition, well, it's necessary to listen to your teacher in order to score 90% or more in extension 2. The negation of an implication then. What we just said was every time we have P, we have Q. So if we're going to negate that idea, that means actually we have P and we don't have Q. P didn't actually imply Q. I had P and it didn't result in a Q. So I have P and I don't have Q. So that's equivalent to not having P implies Q. Converse. Basically, it's the reverse of the implication. So to find a converse, you reverse it. So the converse of P implies Q is Q implies P. Just read it back the other way. The converse of a true statement may or may not be true. Doesn't necessarily have to be true. P is sufficient for Q, whereas Q is necessary for P. So what we're saying here, the converse of a true statement may or may not be true, but similarly, the converse of a false statement may not be false. It doesn't have to be. Here's the example. X, we're going to make the statement, it is raining. Y is the statement, the grass is wet. These are our two things. Now, it might well be true that X implies Y. Right? It is raining, then the grass is wet. It's probably going to be a true statement. You know? However, it's not necessarily true that Y implies X. If the grass is wet, then it's raining. Well, no, maybe someone turned the sprinklers on. So it's not necessarily true. Equivalence then, they're our if and only if statements. So the word if spelt with two F's, which we see a bit in maths. I don't know that you see it a lot of other places, but that IFF means if and only if. It's equivalence. It's the double-ended arrow because that is when both the implication and the converse are true. So P and Q are equivalent statements. So two statements are equivalent if one is the consequent of the other. If they're both, you know. Here's an example of that. I've got a statement, ABCD is a parallelogram. There's my statement. I have another statement, diagonals AC and BD bisect each other. Now, if you remember from your geometry, well, it is X implies Y. That certainly is true. If ABCD is a parallelogram, we are allowed to conclude that the diagonals bisect each other. That was one of our geometry theorems. But the reverse is also true. If I wanted to prove something as a parallelogram, I could show that the diagonals AC and BD bisect each other. So if AC and BD bisect each other, I could conclude that the shape was a parallelogram. So it works both ways. So they are equivalent statements, if and only if statements. So X is equivalent to Y. Oh, in words we'd write it that way with the IFF. So ABCD is a parallelogram if and only if the diagonals bisect each other. Contrapositive. So this may well be a new word here. Contrapositive. The contrapositive of an implication is when you negate the converse. So if my original statement, P implies Q, P implies Q. Then the contrapositive statement is not Q implies not P. So you negate the converse. Now, converse, you read it back the other way, but we negate both statements. Now, the beauty of that is these are equivalent statements. So when it comes to doing a proof, P implying Q, they might have asked us to prove this. But actually, it might be a lot easier to prove that not Q implies not P. Because if I can prove that, then I can say, well, therefore P implies Q by contraposition. So it's another type of proof that we're going to look at that we haven't seen before. A proof by contraposition. An implication is logically equivalent as the same thing as its contrapositive. Okay? Here's an example of that. X is the statement, a polygon is a triangle. Polygon's a triangle. And I have another statement, the interior angle sum is 180 degrees. Well, X certainly implies Y. If a polygon is a triangle, then the interior angle sum is 180 degrees. That's true, I can make that statement. But let's have a look at the contrapositive statement. The contrapositive statement, if the interior angle sum is not 180 degrees, then the polygon is not a triangle. Well, that's true, right? Because if the angle sum is not 180 degrees, we can't be talking about a triangle. So they are equivalent statements. So I could prove either. So X implies Y is the equivalent to not Y implies not X. I'm going to take a look at this thing called truth tables. Now, straight away I just want to tell you something. Truth tables, by the way, not in the syllabus. Okay? Don't know why. I do not understand how you can have any course on logic without talking about truth tables. You know, talking to teachers from other schools as well, a lot of us, we just do it because it just makes sense to do it. So let's see, what is a truth table? In order to do a truth table, you need to put a few things up. These were all the different things we talked about. P and Q, of course, are propositions. But then we could have the negation. We could have and, we could have or. P implies Q and P is equivalent to Q. They were the key things we looked at. And we said our propositions could either be true or false. Let's say P is going to be the statement, I don't know, the cat is white. Q is the statement, the dog is black. Okay, might be true, might be false. So what are our possibilities? The possibility is that they're both true. Okay, so if they're both true, what is the negation? I didn't bother doing the negation of both of them, so the negation of P then must be false. What is P and Q? Well, if I have P and Q, and P's true and Q's true, then P and Q must be true. P or Q. Well, if I have P or I have Q, it doesn't matter which one I have, the answer is true. P implies Q. Well, yes, that is true. Remember, P implies Q. If we have P, we must have Q. Well, if P's true, Q's true, yes, that works. And P is equivalent. Well, yes, they have the same value. What happens if P is true and Q is false? Well, the negation of P still becomes false. But now P and Q is false because we have true and false. So we do not have a true statement now because one's true and one's false. So it becomes false. P or Q stays true because one of them is true. So P or Q is true. P implies Q becomes false. Because remember we said P means we have Q, but we're saying Q is false. So P implies Q would be false. And P being equivalent to Q, well, that's not true. One's true, one's false. So that becomes a false statement. The next possibility is that P is false and Q is true. The negation of P would be true. Again, P and Q would now be false because one's true and one's false. P or Q is true, one of them is true. P implies Q is okay, because remember we said we could have Q without P. That was alright. So Q is still true, so P implies Q, that would be true. And equivalent, again, they're not equivalent because one's true, one's false. If they're both false, the negation is true. P and Q is false. P or Q is false. Neither of them are true. P implies Q would actually be true now. Because P implies Q, well, we don't have either. That's fine. So that's true. And they're back to being equivalent again. They're now false. So I guess the key thing is, if you look down the columns, P and Q, the only time it will be true is when they're both true. P or Q, now it's the only time it's false is when they're both false. Okay. P implies Q, the only time it's false is when Q is false and P is true, so true, false. And in the last one, well, equivalent, obviously they're both true or they're both false is when they're true. Here is your task, because you'll note I haven't put the answers there for you. This is what you're now going to work on. Here is our problem. You can use a truth table if you wish, or you can try and work it out by logic if you wish. Alfred Kurt, the dreaded Kurt, who we all love, Alfred, Kurt and Rudolph are accused of stealing and selling copies of an exam. At the inquiry they testify as follows. Alfred says Kurt is guilty and Rudolph is innocent. Kurt says, well, if Alfred is guilty, then so is Rudolph. Whereas Rudolph says, hey, I'm innocent, but at least one of the others is guilty. Okay? There's our three statements. The first question is, can everyone be telling the truth? Is that possible? Then the next thing to work out is, well, if everyone is innocent, who lied? And assuming everyone's testimony is true, assuming they all speak the truth, then who is the guilty person? So the fourth one was, if the innocent tell the truth and the guilty lie, who is the guilty? How would I approach it? Okay, I've got to break it down into propositions. So my proposition is simply going to be three different propositions. I'll say A for Alfred is guilty, K, Kurt is guilty, R, Rudolph is guilty. It's either going to be true or false. I will now set up the truth table. So the three propositions, A, K and R, and then I have to translate Alfred and Kurt's and Rudolph's statements into logic. There are all the possibilities we could have, all the different permutations of it, true, 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 false, and so on. So all of these are the ones that I could then test. Now, Alfred, there it is. Alfred's statement was, Kurt is guilty. So we have the proposition K. And also said, Rudolph is innocent. So we have the negation of the statement R. So we have K and not R. So I fill it in. Well, K, I just copy across all the possibilities for K, but for R, I'm going to negate all the possibilities for R. I then have to go through and. When do these become true? When do these become false? We said the only time it was true was if they're both true. Therefore, all the others are now false statements, all those false statements. Okay, Kurt. A implies R because Kurt said if Alfred is guilty, then so is Rudolph. So A implies R. Copy through the A's and the R's. Well, when were these ones correct? Well, the only ones that were false was true implies a false statement. That was the only one. All the others are true. Rudolph, his one was a little bit more involved. Rudolph said, I am innocent. Well, that was easy enough, so negation of R. And the next one bit was, but at least one of the others is guilty. So it's either A is guilty or, so A or K. So I have Rudolph not being guilty and I have the situation that either A or K. Well, just like in maths, we work inside out. Let's fill those in. The A or K, the only ones that were false were if they were both false. Therefore the others are true. But now I'm matching up all those blue ones with the not R. So again, I've got false and true, true and true, false and true. Well, the only ones that were true is if they were both true, the rest are false. Now I'm just looking at the red columns. I should now be able to answer each of the questions. Can everyone be telling the truth? So I'm looking for something where everyone is telling the truth. Here it is. Can everyone be telling the truth? Here we go. Look, true, true, true. All three of them come up true. So yes, it is possible for all of them to be telling the truth. If everyone is innocent, who lied? If everyone is innocent, that means all three statements are false. So I'm looking at the false, false, false. Who lied then? Who has made false statements? Alfred did and Rudolph did. Assuming everyone's testimony is true, who is guilty? So now I go to the one that's true, true, true. Everyone's testimony is true. So we've got true, true, true. Slide along. Who is guilty? Well, the statement that Kurt is guilty is the correct statement. So Kurt, that evil Kurt. The fourth one. If the innocent tell the truth and the guilty lie. The innocent tell the truth and the guilty lie. So what are we looking for? We want a true statement coming from innocent people. So it's true here, but their statement is false. Where is it? And there it is. It's that row right there. Because the innocent tell the truth. Look, Kurt this time told the truth, and Kurt's statement was false, so he was innocent. And the guilty lie. Alfred gave a false statement, but it's true here that he was guilty. Rudolph, same deal. So who's guilty? Both Alfred and Rudolph were guilty in this situation. That's the heart of a truth table. It's not, and I've sort of taken it to a really hard question, but it gives you the power of a truth table when it comes to finding these things. By the way, how did we go? Did we get them out? Did you get them out? Okay. Oh, well, the last one is the hard one. That's no question about it.